In a time where AI seems to be getting reduced to sending HTTP requests to an LLM, we are going to go back to the basics. Back to when training models was done on your CPU, and when you had to use a neural network, you also had to implement your own backpropagation. So the goal of the series is to implement a PyTorch-inspired deep learning framework from scratch in C++ to gain more insights into how deep learning actually works, and then eventually use this framework to train our own MNIST classifier. Okay, this is going to be a very exciting episode, as it's also the last episode of this series, and we are finally going to be training our neural network in C++. But let's just quickly summarize everything we have been doing so far, as we have done a lot. In the first video, I implemented a neural network in PyTorch, and the goal of this was to use this neural network to recognize and predict the MNIST digits. And this also showed us which functionality we eventually wanted to support with our own deep learning library, as we want to recreate this neural network in C++ and train it, which is exactly what we are going to do today. Then in part 2 we started working on our C++ library. The first thing we did was create a tensor class, which represents the core building blocks of all the operations in the neural network. Both inputs, outputs and operations of the neural network are done on tensors, which are just, you can see them as vectors or two-dimensional vectors or scalars on which some operations are defined. So we implemented this class in C++, we implemented a matrix multiplication and an addition operation, which are the only two operations we basically need for our neural network on the tensors. Then in part 3, we implemented it in such a way that each tensor also keeps track of the entire computation graph that led up to that tensor, which will eventually be necessary in the backward pass. And in the backward pass, we also implemented a backward method, which will iterate in backwards order through the computation graph and update the gradient of each tensor. So the gradient of tensor 5 with respect to tensor 7. For example, using the grad_fn function, which is capable of updating the gradients of the parents of each tensor. And we did a lot of manual derivations for these grad_fn functions, so definitely watch part 3 of the series if you're interested in that. Then in part 4, we defined another more higher level building block for the actual neural networks, and that is the module. And we implemented a couple of modules. We implemented a flatten module, which, given a input of any dimension, reduces it to a single dimensional output. We also implemented a linear module, which, given a one-dimensional input tensor, will multiply it with a 2D tensor W and then add a tensor, a bias tensor to it to get an output. We also implemented a ReLU module, which turns negative numbers to 0 to introduce non-linearities in our neural network. And then in our previous video, we defined a loss function, the cross entropy loss, which measures how bad our network is doing. And when we do that, and we also had implemented already some way to calculate the gradient with respect to the loss for each tensor. And now that we had both these capabilities, we could implement stochastic gradient descent, which is able to update the weights in such a way that the loss goes down. So now we have finally reached the final part of the series. I've been working for more than 6 weeks on this, both implementing it, creating these videos. So I'm very glad that we reached this and I can finally put my neural network on the treadmill and see if it actually learns or not. So let's first take a look at how we implemented our training loop in PyTorch, as this will guide us with our own C++ implementation. In PyTorch, what we did is we first defined a certain number of epochs, which represents how many times we are going to go over the entire training data set. You don't want to do this too much, as one, it slows down the learning, because you are just iterating more times over the training data set, and you also risk overfitting on the training data set. But anyways, for each epoch, we are first going to train on the train set and then going to test on the test set, so that we can also see if, for example, the training loss goes down. So we see, okay, our network is training, but you also see that the test loss actually goes up, or the test accuracy goes down, so that on the test set we are not performing that well. Then you can actually conclude that we are overfitting on the training set, and that's not good, because we want to generalize. So anyways, that's why for each epoch we both go through our training set and our test set. Actually, in real life, you should do this with a validation set, but there are just some details. The train method looks as follows. It takes the training data loader. In the training data loader, what we are going to do is we are going to iterate. It will give us batches of data, as the actual data is split up in batches of a certain size, and each batch will, for example, if the batch size is 10, will contain 10 training images, which are the axis, and also the 10 corresponding labels, which is represented by the Y here. In PyTorch, you can actually put an entire batch in through the model, and it will be processed in parallel. We didn't implement this for our C++ framework, so you will see how we are going to handle that later in this video. But in PyTorch, you can just pass multiple images at the same time through our model. Then we get a prediction for each model. We can then calculate the loss with this prediction, which will compare the predictions with the real labels. We can then use this loss to calculate the gradient of each parameter in our neural network with respect to the loss, such that we can then in our optimizer improve, adjust the weights of our neural network in the direction opposite to the gradient with respect to the loss, so that the loss actually goes down. And finally, we just turn the gradients back to 0, as we don't want the results of one batch, in this case, to impact the gradient of the other batch. In the test set, we are going to do something similar. We are going to iterate over the test set, which is once again going to give us a batch of images and labels. We are going to get predictions for that batch, and we're then going to also calculate a loss, but this time it will be called test loss, and we will also be calculating the accuracy by looking at which number, which index on the output tensor gets the highest number. So we take an argmax, and this will give us the index back on the tensor with the highest number, and this index represents then which class the network has the highest confidence in, and then we can use this to calculate an accuracy, because we can just check if this is actually equal to Y, which is the real label. And then we can also log the test accuracy and test loss. And if you have been following the series so far, you should know that there is something about this that we haven't implemented yet, and that is actually this data loader and how to load in our actual data. And the data sets that we want to use are the MNIST dataset and the Fashion-MNIST dataset. The MNIST dataset are black and white images of 28 by 28 pixels, where the labels are between 0 and 9, and each image represents a single number. And the Fashion-MNIST dataset, which is a drop-in replacement, so once again 28 by 28 black and white images with 10 different clothing items, and each image represents a clothing item. And this task is a bit more difficult than recognizing numbers, as also as a human sometimes it's pretty hard to see, for example, what a certain item actually is. But anyways, let's take close to how PyTorch does this. And first we need to find a way how to load our dataset from disk into in PyTorch. It's in Python, but we need to load it from disk in C++. But anyways, in PyTorch, what you need to do if you want to use a certain dataset is you need to subclass dataset class, and you are required, as you can see here, to implement a couple of methods. The most important being the getItem method, which given an index returns a image and label for that index. So you need some way to load in your data in such a way that each index corresponds with a single item of your data set. And that's often being done in the init method. You can also already load in your data here, which is what we will be doing. As you can see in this example, they are reading in a CSV to already have a list of labels, but the actual image, they only read that in when the image is asked for. But these are just implementation details. You can decide for yourself how you implement these methods, but you're just required to implement them. What we actually want to do based on this is we have on disk here MNIST dataset, and if you unzip them, you get this, both for the Fashion-MNIST and the MNIST. The T10K is the test set, and the first is the images, and the second file will contain the labels. You will see that this is a binary file containing everything in binary, and it's also called EDX3 and EDX1, which are some very exotic ways to represent, to serialize your data, but more on that later. So as I said, these are stored, these are just stored in binary. And what we want to do is being able to call getItem and with an index, and then actually get returned in integer in C++ with the label, and a 2D tensor with our own tensor class, which represents an image, which in our code will be a 28 by 28 tensor with floating point numbers representing how dark a pixel is at a certain location. But one advantage of PyTorch and Python in general is in PyTorch it's very easy to load in the Fashion-MNIST and MNIST datasets, as you can just call, as it's already implemented for you. You can just call datasets.fashion-MNIST point where the data needs to be downloaded, and it will just load everything in for you. And also, if you look into library code, what they do is just call a read image file method. And one thing I've noticed is that in C++ there isn't a lot of I think it's much harder to share code, so it's much harder to already find some code that reads these MNIST files, and you have to do a lot more manual work, which is a bit annoying, especially as this EDX file is fairly unique. And I think it was defined by Jan LeCun when he made this paper where he used the MNIST dataset. But when I try to go to a site where the format should be explained, often it just gets blocked, which is like, how do you even start with reading in this binary file then if you don't know how the data is actually written here? So what you do, you once again go searching on the internet, and eventually you find some people who will luckily explain to you what this format of this file actually looks like, and for example that the first bits represent the magic number to check if the dataset is loaded correctly, then the number of samples, so the number of images is written, then the actually rows and columns of each image, as I said it was 28 by 28, and then followed by the actual data. So if you don't know this, it's very hard to actually read in even your data. And even this, I'm not used to low-level languages, so what I did was I once again got on Stack Overflow and found someone else who has having a lot of trouble with reading these MNIST digits in C++, and I found some good code right here which I could adapt a bit. And as you can see, you need to do some tricks like reversing the numbers you are reading, because they are, I think, stored in big endian and they need to be in little endian. So you need to reverse them like this, but like a lot of low-level stuff that you don't even think about when trying to train a neural network, and you also don't want to think about. So I'm really glad that I could just get inspired by this code and adapt it a bit. So let's get started with the implementation of our dataset class. We are going to start by creating a base dataset class with a purely virtual getItem method, which given an index should return an integer label together with a pointer to a tensor which represents the image. We also add a purely virtual getLength method. Just like in PyTorch, all datasets should be a subclass of this abstract base class. Inspired by PyTorch, we can also define an MNIST dataset class inheriting from the base dataset class. This MNIST class will need private variables for holding the images and labels, which will be loaded from disk, and also has class variables which contains textual labels for the different classes. The constructor will take as input a path to the MNIST image data as well as a path to where the labels are stored. The constructor will just call both a readMNIST and readMNIST labels method and store the outputs in the corresponding variables. The readMNIST method is heavily inspired by the Stack Overflow code I showed you earlier, as it contains a lot of low-level logic, such as reversing big endian numbers and parsing it into an integer. Things like that showed me that even just loading data in C++ is somewhat complex. So what the code does is it will just load in all the images that are stored in binary in the images EDX3 UByte and turn them into vectors of floating point numbers, such that we can eventually return them as tensors in our getItem methods. The readMNIST labels method takes as input the corresponding labels of the MNIST dataset we want then to parse into integers, so the output of this method will be a vector of numbers between 0 and 9. Now let's also define a getItem method, which given an index is able to return a tensor of the image and label we store at that index. The implementation is very straightforward. Just use the index to create a pair of a label and a tensor by using the passed index. Finally, we override the getLength method to give us back the amount of samples in our dataset, and we also implement a label-to-class method, which given an integer label will return the corresponding string we defined for that label. As we also want to train our model on the Fashion-MNIST dataset, we are going to create a Fashion-MNIST dataset class. This will be entirely the same, except that it's going to contain different classes, this time the 10 different clothing items. Let's also implement a visualizeImage method to turn a tensor of an MNIST image into an ASCII representation. This is a bit scuffed, but I didn't want to have to install and learn an entire visualization library just to visualize some MNIST labels. But just having a dataset isn't enough. We also need a data loader, and what a data loader also in PyTorch does was it takes as input a dataset, a batch size, and whether we should shuffle the dataset or not when before dividing it into batches. So in short, it can be summarized as follows. We have a dataset we load in, but then we also want to shuffle the dataset first. And this is done because in each epoch, we don't want the network to see the same samples in the same order, because it could then also learn the order and that could impact the generalization of our neural network. So we always want to first of shuffle our dataset in each epoch. And then we also want to divide it into batches, which this data loader will then do. So for example, if batch size is 2, the whole dataset will be divided into batches of 2, and the data loader will then provide us also with an easy method to just iterate over the data loader and get a batch at each time. So that also, the training process is very easy. So let's implement that. Our data loader class will hold a pointer to a dataset. It will also store a batch size and a vector of indices, which are used to determine the order when iterating through our dataset. Our constructor will take as input a pointer to a dataset, a batch size, and a boolean indicating to shuffle our dataset or not. For the implementation, we will assign the dataset and batch size to the past values. We will also create our indices vector, which will contain the numbers from 0 up until the length of our dataset -1. The purpose of this indices is mainly that we can now shuffle this indices vector and can then use it to access our dataset in shuffled order. Just like in PyTorch, we want to be able to iterate over all the batches of our dataset in a for loop, so we are also going to implement an iterator class. This iterator will hold a pointer to our data loader and an index. The constructor of the iterator will just assign these variables. Also, every iterator will need to implement the ++ operator, which in our case will increase the index of our iterator with the batch size of the data loader. We are also required to implement the star operator to return the batch at that specific index. This will be a vector of labels and image tensors representing the current batch. We can easily construct this by starting from our current index of our iterator and then getting the next batch size items from our dataset. By also using our indices vector, we are keeping the shuffled order. Finally, we need to determine when to stop iterating. This is done by implementing a not equals operator, which will be giving an iterator which has an index equal to the length of our dataset. And as long as the index of our current iterator isn't equal to that index, we haven't iterated over all the batches of our dataset. We also need to implement a begin method, which will return an iterator containing the current data loader and an index set to 0, and an end method, which will return an iterator representing when we need to stop iterating and will thus be used in this not equals operator. To finish things off, we are going to implement some methods to return the batch size, the amount of samples, and the amount of batches. Let's now quickly test that everything is working by creating a dataset and data loader and visualizing some images and labels. Everything seems to be loaded correctly, and this ASCII visualization is actually kind of cool, I think. Okay, so now we have implemented everything we need to start training, and this training process will look as follows. We are first going to define a neural network. We are then going to define an optimizer, which takes as input the parameters of this neural network. We will then, for a certain amount of epochs, iterate over each batch of our training data. First off, pass this batch through our neural network to get predictions, use some kind of loss function to give in these predictions and the actual labels, true labels, calculate a loss. We will then call loss.backward to calculate the gradient of the loss with respect to each parameter of our neural network. We can then, after we have calculated the gradients, update the actual parameters of our neural network with our gradient descent optimizer, which will use the gradients to push the weights in the opposite direction of the gradient. And then finally, we will call the zeroGrad method to put each gradient back to 0, so our network is ready to process another batch. And let's see how we are going to translate this into C++. We had already recreated our PyTorch neural network in a previous video, but let's quickly go over our architecture. Our neural network has a flatten layer, which will turn our 2D image input into a one-dimensional tensor. Then we have a series of linear layers. The first layer will take as input this flattened image, so it needs to be able to take as input a 28 by 28 flattened, so 784 numbers, which then represents the amount of pixels in the input image. After multiplication with a 2D tensor and adding a bias to the output, The output will be a one-dimensional tensor of size 512. This output is then passed through a second linear layer and eventually a third, so that our final output is of size 10, which then represents the confidence of our neural network in each of the 10 possible label outputs. We also define a ReLU activation function to introduce non-linearities in between the layers. In our constructor, we register all the modules, which will allow our optimizer to know which weights need to be trained. Our forward method will then take as input a 2D input tensor representing the image, we flatten it, and then pass it through a chain of linear and ReLU layers to eventually return the output tensor. Let's now implement the method to train our neural network. First, we will have to load our dataset. I have already downloaded both the MNIST and Fashion-MNIST dataset, so let's load the train and test set. I will first train a regular MNIST model. I will be taking a batch size of 10 and create a data loader both for the train and test set. We are going to create an instance of our neural network, define our cross-entropy loss function, define our stochastic gradient descent optimizer with a 0.001 learning rate, and it also gets as input all the trainable parameters of our neural network. Let's train for 3 epochs. This is the amount of time we will be iterating through our entire data set. For each epoch, we will be first training the model on the train set and then test our model on the test set. This way we will know if our network is overfitting. This would be, for example, the case if we see the training loss going down, but also the test accuracy decrease. Finally, we save our trained model so that we can load it in at a later time. We now have to implement the training logic that will be executed each epoch. We first create some variables which will help us with logging our training progress. Then we iterate through each batch of our training set. As we can't process an entire batch of samples in parallel like in PyTorch, we will have to iterate over each label and tensor in the batch one at a time and accumulate the losses by manually summing them for each sample in the batch. But the core logic will stay the same. So for each sample, we will pass the image tensor through our model to get an output containing the confidence of our neural network in each possible output class. We then pass this output tensor through a loss function together with the true label to calculate how good the prediction of our neural network is. Because we don't offer batch processing, we will add our loss to a total loss variable and then repeat this for each sample in the batch. We log the loss for the batch. We will call the backward method on the total loss, which will calculate the gradient to each parameter of our neural network. Call the optimizer step to update the values of our network parameters based on the gradient. And finally set all the gradients to 0. So this is our training loop, which will optimize our neural network to decrease our loss and make our network recognize MNIST digits. Let's also implement a method to calculate our loss and accuracy on the test set for each epoch. We will just loop through all the batches of our test set, loop through each sample in the batch, pass it through the neural network we are training, take the index of the output to which our neural network assigns the highest number, which will be the prediction of our neural network, and check if this was indeed the correct class by calculating the accuracy and loss metrics. Okay, so this is the moment we've all been waiting for. We are finally going to train our MNIST model. I have also quickly written an inference function which we call later, which will load in our trained model. It will then load in the test set once again. It will allow us to sample, in this case, 10 samples of the test set, and it will then pass these samples through our neural network, the trained neural network, to get a prediction, and it will log the predicted class and the actual class such that we can eventually also manually check a bit if our network indeed did learn. But anyways, we are going to train for one epoch with a batch size, no copilot, with a batch size of 10. So let's quickly build our project, and launch it. The dataset is being loaded in. And you can see we start training. We are logging every 1000 samples, and you can see the loss of the first batch was 2.3. If you have seen the first video, you should notice by now that things are running a bit slower than our PyTorch implementation. So let's quickly maybe also train another PyTorch model. So this is the code from the first part. We are going to load the MNIST dataset. We are also going to use a batch size of 10. Let's visualize the data a bit. These are our usual MNIST samples. We are going to use the MPS device, which is the GPU of my MacBook to train. Let's define our neural network, our loss function, our training methods. Let's train, in this case, for 5 epochs. And you will see how fast that our neural network basically is training. We are processing these samples so fast. Let's open it. And if we look at what we did in PyTorch, in our own C++ framework, we've only processed 1000 samples, while here we've already processed an entire epoch. So what is happening here? Why is this running so much slower? You probably think C++ is a very fast language, so why is this Python library running so much faster? First off, under the hood, PyTorch is also written in C++, so it's just the heavy lifting is not done by Python. And you should also realize that we have written our C++ framework in a very naive way. For example, when we are multiplying matrices, we are just iterating over 3 loops and then multiplying numbers one by one. Also in our training methods, we are, let's see, when we iterate over a batch, we then iterate over all the samples one by one and input them one by one in our neural network. While in PyTorch, what we are doing is just taking the entire batch and passing it in one time through our neural network. So in short, we are just processing things one by one, and that is also the naive and normal way how you do things on a CPU, but there are many low-level optimizations, for example, that are called, when you're training on your CPU, that are called single instruction multiple data, so that in a single CPU instruction, multiple data can be processed in parallel. This is, I don't know, I've not looked into how I should implement this, but it seems pretty advanced. And this allows you to do multiple operations at the same time. So we are not doing that, which will slow us down a lot. There are a lot of C++ linear algebra libraries which implement these instructions and allow you to really quickly multiply matrices. But as we wanted to implement everything from scratch, I didn't want to use libraries like this because having already a library that can multiply matrices for you, it isn't from scratch that way. Another thing we are doing in PyTorch and not in our C++ project is using the GPU. If you have an NVIDIA GPU, you can of course train on it, and with our M1 MacBook we have an MPS device. And GPUs are optimized for processing things in parallel, and as many things in a neural network can be done in parallel, GPUs are definitely the way to go, which is also why the NVIDIA stock price is at the moment so high. And in NVIDIA this is called CUDA, so you can use CUDA to write instructions for your GPU. So if I would have implemented this in CUDA, it would run much faster, but I have an M1 MacBook so I only have access to this metal performance shaders. I've not looked into it that much about how it works, but as you can see, they contain some examples on how to train a neural network with it. But once again, I wanted to implement everything from scratch for this series to really dive deep into how it's done and not, I've not looked into how to optimize the performance, but using metal performance shaders is definitely the way to go if you want to get the maximum performance on MacBooks. And the last thing, which we probably didn't do very efficiently, is for all this back propagation, we implemented a CredFN function, but these are also implemented very naively, once again not using any parallelization. And also for things like the softmax, the cross entropy loss, which is just a softmax followed by a negative log likelihood loss, we for example derive both a CredFN function for the negative log likelihood loss and also a CredFN function for the softmax. So these could probably be combined into a single CredFN function, and it are optimizations like this that libraries like PyTorch do under the hood, which makes them much faster. But we see the loss is decreasing, but it's going to take a while to even train one epoch. So let's just wait and see what the final loss will be. So after, I think it was about an hour, our network finally was done training. And also on the test set, we got an accuracy of 94.6%, which is pretty high and also good for MNIST. MNIST is a pretty easy task though, but it's still nice to see that we actually learned to predict it. The model is saved right here. But now let's do some inference on the saved model, and let's see what some random samples will show us. Inference on saved model, let's execute this. And let's look at some predictions of our model. Okay, the number 5, we predict 5, the actual class is also 5. Number 9 is predicted as 9, 1 as 1, 4 as 4, 2 as 2, 3 as 3, 5 as 5, 8 as 8, 7 as 7, and 1 and 1. Maybe let's try some different numbers. Okay, so this one was predicted wrong. We predict 4, but it's actually 8, but you can kind of see why he would predict a 4, because if you would just block off the label, yeah, that's a bit harder. Okay, we also predict this one as 4, which is actually 9. This one is a bit, the shape, maybe he still didn't learn that correctly. 1, 1. It seems like he is confusing 4 and 9 a lot. Okay, this one 2, 2, 8, 8, 6, 6, 4, 4. And 3, 3. So you see he still is making some mistakes. Our network wasn't perfect. He didn't get a 100% score, but most of these he is predicting correctly, which is awesome, of course. So what we are now going to do is train on the Fashion-MNIST dataset, as this one is a bit harder. Let's quickly visualize it and maybe also retrain our C++ model, our PyTorch model also on this. So use Fashion-MNIST is true. Let's divide it into batches. And you see this is the Fashion-MNIST dataset, so we need to predict clothing items. Let's also retrain our neural network here. Okay, so after 5 epochs we get a 80% accuracy, so the test is actually a bit harder than the MNIST dataset. Okay, let's now quickly make it such that we train on our Fashion-MNIST dataset. Let's build our project and let's start training. Okay, so once again, after training for an hour, we finally trained it and we reached 83.8% accuracy, which is slightly higher than the test accuracy that we had when training in PyTorch. So this is that. It maybe takes 100 times as long, but at least we get some better accuracy. Of course, we are not hitting the 95% accuracy of the regular MNIST dataset because this is harder. So let's see. Okay, our model is now also correctly saved. So let's also try to do some inference on our saved model and see which kind of mistakes that we make. Okay, so okay, this is a pullover. We predicted this as a pullover. T-shirt top, predicted it as t-shirt top. It's kind of deformed because we are printing it in ASCII art, but yeah. Coat, we predicted as a coat. Ankle boot, correctly predicted as ankle boot. Once again an ankle boot. Pullover, sneaker, predicted as sneaker. Coat, yeah, pullover, predicted as coat, but yeah. Pretty hard, as you can see. Once again, like this is a code and this is not a code, but we both predict codes and one is correct. Sandal, predicted as sandal correctly. Let's run it one more time. We predict this as a t-shirt, but yeah, it's actually a dress. We predict it as a shirt, but it's a bag. Of course, the ASCII art isn't that accurate to when I would just visualize it like, yeah, things like this in MNIST. So our model actually has some more data than when we reduce it to ASCII art. But anyways, we predicted wrong. Shirt, shirt. T-shirt top, we predict t-shirt. I feel like there should be some, yeah, that we still get some points for that because we are closer. Sneaker as sneaker, trouser as trouser. I think trousers are pretty easy to predict. Bag as bag. Ankle boot is, we predict this to be an ankle boot, but it's a sneaker. You can see the silhouette is kind of close. Ankle boot predicted as ankle boot. Dress as dress. So you can see our network is definitely learning. It takes a lot of time, but eventually our backpropagation is working and we can actually train models this way. Okay, so we have done everything we wanted to do. We rebuilt our entire PyTorch network in our own C++ library. We are capable of training it on the MNIST and Fashion-MNIST dataset, and we got good results, although the training takes a bit long. So I definitely learned a lot with this series, and I hope you did as well. If you still have some questions, leave it down below. In the future, I might try to optimize this by, for example, using this MPS library to actually train on my MacBook's GPU and see how well our framework would perform if I would change it a bit such that it's actually optimized. But anyways, I hope you enjoyed the series, and if you like machine learning videos like this, consider subscribing, and I see you in the next one.